Determine the Laplace transform of t times sine of bt. So what we can do here is we can take a look at sine of bt, and we can actually call that f of t. And what we should recall from the previous video, that the Laplace transform of sine of b times t is given by b over s squared plus b squared. In other words, if we call that f of t, we can write that f of s, the Laplace transform of sine of b of t, is actually equal to b times s squared plus b squared to the power negative 1. So I'm writing this fraction as a multiplication because I want to take the derivative next time and I don't want to use the quotient rule. So I'm going to write this division as a product. Okay, so we're going to take the Laplace transform of t times f of t, sine of bt. And by the previous theorem, if you multiply your function times t, you have to, since this is t to the power 1, we have to multiply times negative 1 to the power 1, and then we take the derivative of f of s. So capital F of s. And now we're going to write that as a product, right? And b is a constant. That doesn't depend on s. And so that's something that I can pull outside the derivative here. So I actually end up with negative b, and then the derivative of f of s is s squared plus b squared to the power negative 1. And to take the derivative, what is going to happen is that to the power negative 1, I'm going to subtract 1, and I'm going to move that negative 1 to the front. So I'm going to have times negative 1, and then s squared plus b squared to the power negative 2. Now, I then still have to multiply by the derivative of the inside function. So I have to multiply by the derivative of s squared plus b squared. That's my chain rule. Now, the derivative of b squared is the derivative of a constant, so that's 0. And the derivative of s squared, that's 2s. So let's combine what we have so far. we have negative b times negative 1. That gives us positive b. And then we have what we can write as 1 over s squared plus b squared squared. And then the derivative of that is times 2s. And when we combine all of that together, we get 2b times s all over s squared plus b squared squared. So that is the Laplace transform of t sine b of t. And since the original transform is of exponential order 0, we can say that this is for s is s greater than 0. Now, for easy reference, the following table lists some of the basic properties of the Laplace transform. We already saw 2 of them in the previous section that have to do with the linearity of the improper integral. So the Laplace transform of f plus g is the Laplace transform of f plus the Laplace transform of g. Laplace transform of c times a function f, where c is a constant, is c times the Laplace transform of f. Then we have the translation in a. The Laplace transform of e to the power at times f of t is the Laplace transform of f at s minus a. And then Laplace transform of f prime, we have the Laplace transform of f double prime, and more generally, the Laplace transform of the nth derivative. So this is theorem 4, and this is a special case of theorem 5, and this is the general case of theorem 5. And then we also just did an example where we use the fact that the Laplace transform of t to the power n times f of t evaluated at s is negative 1 to the power n times the nth derivative with respect to s of the Laplace transform of f. Now, finally, for Laplace transforms in this section, we'll determine the Laplace transform of sine squared t. And sine squared t is not in any table that we've seen so far. And it would be maybe tempting to say something like this. So is the Laplace transform of sine of t times sine of t, is that the Laplace transform of sine of t times the Laplace transform of sine of t? And that is not correct. So that does not hold. So what we can do here is we can use a trigonometric identity, and the trigonometric identity we'll use is the trigonometric identity for cosine of 2t, because that is equal to 1 minus 2 times sine squared t. And so this is something that we can solve for sine squared. And so we see that we can rewrite sine of t, or sine squared of t, as 1/2 minus 1/2 cosine of 2t. And so when we're finding the Laplace transform of sine squared of t. We just replace that by the trigonometric identity. So that's the Laplace transform of 1/2 minus 1/2 cosine of 2t and what we're then going to do is use the linearity of this Laplace transform. So I'm going to write this as 1/2, right? That's a constant multiple. Can write this as 1/2 times the Laplace transform of 1 and then I can subtract from that. So then I have minus 1/2 times the Laplace transform of cosine of 2t. And then I can use the table and find that the Laplace transform of 1 is 1 over s. So that is 1/2 times 1 over s. And then minus 1/2. And the Laplace of a transform of cosine 2t is something that you can look up in a table as well. And that is s over s squared plus 2 squared. And so when we combine all of that, we get 1 over 2s minus s, get s over 2s squared, and then 4 times 2 is plus 8. And that is our Laplace transform of sine squared of t.